Cool. So we are recording. So today, what we're doing is if you read the background section, we're talking about this thing called the Great Debate, which is these two guys, Shapley and Curtis. They were two astronomers, and way back when they had a debate about the size of of our galaxy, not our universe, and also where we are in our galaxy. And so I always like to start off with this picture. This is a really good picture because if you've ever seen a night sky that's this dark, then you've probably seen some segment of the Milky Way strip here. That's us seeing out of the spiral that is our galaxy. Um, but there's this other blob here labeled the LMC. That stands for the Large Magellanic Cloud. And that was a big topic in this debate is what is this thing, this blob that we see in the sky? Is it just some sort of nebula or is it an actual galaxy super far away? And in this context, looking at this picture, it's really hard to tell, right? So that's what these guys were arguing about, and that's what you're going to be looking into today. So let me go back to the lab itself here. So these are the two astronomers who had this debate, Shapley on the left and Curtis on the right. And there were a couple of things that they argued about specifically. So Curtis, he figured that our position in the galaxy, that we are at basically the center of our galaxy, right? That was his assumption, whereas Shapley thought that we were not at the center of our galaxy, that we're somewhere out on the edge of the disk maybe, or somewhere in between. Not only that, but Curtis thought that the Milky Way was pretty tiny. He said about 10 kiloparsecs in diameter, which a kiloparsec you may think is large, but it's pretty small, especially compared to what the Milky Way actually is. And Shapley, on the other hand, he thought that the Milky Way took up basically the entire universe, that almost the galaxy was the universe, and it was about 100 kiloparsecs across. And one thing that kind of differentiated their opinions was this thing, or these things called spiral nebulae. And again, that's what that LMC was in the picture that I showed. We see these things in the sky, and Shapley and Curtis were arguing whether or not these blobs in the sky that we saw, these what looked like nebulae, whether or not they were far away from us, like outside of our disk, and comparable in size to our galaxy. So what you would think another galaxy would be like, we have our galaxy, and then super outside of our disk is another galaxy of basically the same size. That's what Shapley thought was the case, whereas Curtis, actually I might have that backwards. Curtis was the one who thought that these spiral nebula were super far away and big. They were comparable in size to our actual galaxy, whereas Shapley thought that these spiral nebulae were interior to our disk and smaller than our disk, right? They were just kind of vibing around in our Milky Way. So what you're going to be doing today is investigating their arguments for yourself and determining which one was right about what. So the first part that you're going to be doing is you're investigating where we belong in our galaxy. Are we at the center of our galaxy, or are we somewhere around the outer rim of it maybe? And to be doing that, you're going to be mapping these things called globular clusters. This background section talks a little bit about how globular clusters are formed. You have these huge clouds of dust and gas, and you have these little grains, and through gravitational collapse, they'll slowly get closer and closer together, start kind of a snowball effect where they start building up stars, right? So you have this huge cloud of dust and gas, and it eventually collapses down to form a big group of stars. And that's all well and good, but that doesn't happen everywhere in our galaxy. The reason for that is our galaxy has different structures. You have the big disk that everyone knows and loves, and that's spinning right around its center. So if I have one of these clouds of dust and gas that is near the disk, like if this is the plane of the disk, and I have one of those balls of gas and dust in the plane of the disk, and it's trying to condense down and form into stars, the disk is spinning right around the center. And that angular momentum, as this picture is kind of trying to show here, will rip apart that cloud of gas and dust. So you can't really form globular clusters very well in the plane of the disk because that angular momentum is going to rip them apart. So what we see actually is these globular clusters reside more in the halo of our galaxy, which you can think of as just a big kind of imaginary sphere surrounding the disk. And these globular clusters, remember, these are huge groups of stars, but we're considering them as one entity. And they're flying around the center of our galaxy, just not necessarily in the plane of the disk, right? So you can think of it kind of as like a beehive almost. You have all these points flying around some common center. And they may not all be going in the same direction, but they're all orbiting the center. And in this picture, that's what it's trying to show in this picture. They're all occupying the halo of our galaxy and orbiting around this center bulge, right? So what we can do is we can map out the positions of all of these globular clusters. And what we expect is that at the center of our galaxy, there's going to be a stronger, more tightly correlated distribution of these clusters. In other words, referring to this picture here, this is a top-down view of the disk of the galaxy, theoretically. So in the plane of your computer right now, that is the disk, and then you're looking top-down on the disk. So it's like looking at this picture here, and you're looking at the positions of all of these globular clusters at the ends of these arrows, but you're only looking from the top down this way, and you're plotting out where all these positions are. And as you can see, we expect that the distribution of these globular clusters is going to be a lot tighter around the center of the galaxy, right? So what we can do is we can find the positions of all these globular clusters, map them out, and then see where we compare. Our position may be over here, which means we're not in the center of the galaxy, or our position could be right here in the center of that tight distribution, and then that would tell us that we are at the center of the galaxy. So that's what you're doing for the first part. I'm going to skip this next background section really quick and talk about that. So like I said, you're going to be mapping out all of those globular clusters. And to do that, we're actually going to be using the techniques that we learned in the last lab. And I know Grace is probably cringing because it's the last lab and it's complicated, but we make it a lot easier on you in this case. So we're going to be using RR Lyrae stars to calculate the distance to all of these globular clusters that we're going to be mapping out. But we give you everything you need, basically. So this table here, we have a huge table here in the lab of all these different globular clusters. And we give you the galactic longitude and galactic latitude of each of them. You don't have to worry too much about that. All that is just a coordinate system we use to describe the positions of things in our galaxy, and it's centered on us. So we are the origin of this coordinate system, and then it's just like latitude and longitude, as you'd expect, where 0 longitude and 0 latitude points right towards the center of the galaxy. So we are at the center of this coordinate system, and then 0, 0 points this way towards the center. But again, that's not super important. You can just take these values face on and just accept them. The key point here is you're, again, going to be measuring the distance to each of these globular clusters using RR Lyrae stars. And again, we make it super easy on you because we give you the apparent magnitude here of each of those RR Lyrae stars. And then all you have to do is fill in what the absolute magnitude of an RR Lyrae star is, which you should know from Lab 5. If you need to go back and reference it, then that's cool. And then using your apparent magnitude and your absolute magnitude, you can calculate the distance to that globular cluster. Hopefully most of y'all are familiar with that because you've been working on the lab. If you're not remembering it, remember it's that d is equal to 0.01 kiloparsecs times 5.85 to the little m minus big M, that equation. I think that was right. Something close to that. Anyways, you're going to be calculating the distance to these globular clusters. And you can, if you want, go line by line and just enter in these values as you're calculating it. Or if you want to be clever, you can also use a spreadsheet if you're good with spreadsheets. This works well because you can literally, hopefully, just copy and paste all of these values in this table, like so. And then you can copy and paste this into a spreadsheet. Here, I've already labeled my different columns. This is just basically copying down the table in the lab, but you can copy and paste and it will fill in all those values for you. And then if you know how to use Excel, you can create an equation using the values in this row that spits out a number in this cell here, and it'll do it row by row. If you have any issues with that, or if you're confused about how to use Excel, I can help you later after the lecture. But that's the easy way to get through that part of the lab. Is I would advise using a spreadsheet just because it's easier. Or if you want, you can go line by line. It's just easier to make mistakes doing that. Does that make sense so far about what you're doing? Any questions? No? Okay. Cool. So once you have the distances to each of those globular clusters, then you're going to be making a map. Remember, you're going to be making that top-down view of that distribution. And you're going to be doing that using this tool. Go follow this link here. It's not very specific. It just says go to this website. But that'll pull up the plotting tool that you've used in the past. And you want to make sure that you're selecting this scatter option, and that'll bring up something that looks like this. And here you can see that it has the longitude, the latitude, and the distance of each globular cluster. These aren't the correct values. You have to put in your own values, but you should just fill them into the columns corresponding to the same names. And that should plot out a top-down view of those globular clusters. And what we're looking for is where we are with respect to all of those globular clusters, right? So plotted on here right now is actually this yellow circle. That is our sun. So effectively, that's our position in the galaxy, right? And all of these orange dots are going to be the positions of all your globular clusters. So hopefully, when you measure the distance to each globular cluster using all the RR Lyrae stars, you should see some sort of distribution in this plot that looks something like this picture, where there's a tight distribution towards the center of the galaxy. And then you look at your plot and you say, the sun is either far away from that center or close to the center, and that tells me where we are in the galaxy. And it's not going to be perfect. You're not going to see a perfect circle representing the disk, but it'll be some rough distribution. So you're going to have to kind of eyeball it. And so then you talk about how far we are from the center, or if we're directly at the center. And you're also going to be recording the apparent diameter of that distribution. So remember, this is the top-down view. So if you just look at this distribution that hopefully looks something like this here, if let's say this is all the points I have, then I'll say, okay, this distribution here, the big distribution, looks like it's about so-and-so kiloparsecs across. So that's what I think the diameter of our galaxy is. And again, you're going to have to eyeball that a little bit. And then it asks you to talk about comparing your results to what Curtis and Shapley were arguing. So that's the first part. That's just figuring out where we are in our own galaxy, and also how big our galaxy is, the diameter of it. The next part that we're going to be talking about is these spiral nebulae that Shapley and Curtis were discussing. Well, I don't have the picture up, but remember, Curtis thought that these spiral nebulae were super far away from us and comparable in size to our own galaxy. He thought they were basically other galaxies, whereas Shapley thought that they were interior to our own galaxy, and they were maybe like the size of these globular clusters. So you're going to be looking at those spiral nebulae, quote unquote. So that's what this background section here is starting to talk about, is astronomers were seeing these things in the sky. We had no idea what our own galaxy looked like, so we didn't know whether or not these were galaxies or something else. So first thing that you're going to be doing is we want to know the physical size of these objects. If we measure the physical size of it and it's bigger than the size that you got in the first part, then we know that it's not interior to our galaxy, right? Because if something is inside our galaxy but it's bigger than our galaxy, then that doesn't add up. It makes sense if it's far away and big rather than interior and small. Hopefully that didn't confuse anybody. But the point is, we want to be measuring the physical diameter of these objects and see how that compares to the physical diameter of our own galaxy. And y'all might remember this equation from one of the previous labs. I think it was the Galilean revolution, maybe. But again, what we're doing here is we're measuring the physical diameter. To do that, we measure an angular diameter first. That's what we do in afterglow. And then if we know the distance to that object, then we can calculate what its actual physical size is. Because remember, this angular diameter that we're measuring in afterglow, whatever you get in arc seconds or arc minutes or degrees, that's just how it appears on the sky. It's a projection. So you have to take into account how far away it is in order to figure out actually physically how big it is. That's what this equation is doing here for you. So we need two pieces of information. First, we need the angular size, which you get in afterglow when you're doing your red arrow measuring the diameter. And then we also need the distance to that object. When we have both of those, we can get the physical diameter of the object. So to get the distance to the object, we're going to be using Cepheid variable stars, like we did in the last lab. Again, we're making it easier on you here because we're giving you all the information you need. You have all of these galaxies, and each one of them has a Cepheid variable star in it. And we give you the apparent magnitude and also the period of its variability. So you're going to have to remind yourself how you did this in Lab 5 if you've already done it. Again, you're going to be using that distance equation that depends both on little m, the apparent magnitude, and big M, the absolute magnitude. But the key here is that for Cepheid variable stars, if you remember, the absolute magnitude depends on the period. So you have to use this period to calculate the absolute magnitude, and then you are able to calculate the distance to that spiral nebula. Did I lose anybody? Is everyone following? Cool. So then I have the distance to my spiral nebula, and now if you remember, I need to get the angular size of that nebula, and then I'll be able to calculate its physical size. So in this lab, we were supposed to observe these galaxies in Skynet on our own. I was under the impression that we were not doing that anymore because of the coronavirus. The observatory down in Chile closed down. And so I was under the impression that we weren't observing anymore for the rest of the semester. I found out today that we actually can observe as long as we use the telescope that is in Australia, the Meckering Observatory. That's the Prompt MO telescope. So it's no big deal. Y'all still have plenty of time, but I would like y'all to try to observe these galaxies for yourself. Everything you need is here. You have the name that you type into Skynet. You have the filter and the exposure in seconds. The only difference when you open up Skynet is normally when you have this first page open, you would have the Chilean observatory here, because remember, we care about when it's observable if we're looking at this plot down here. So we want to make sure it's observable from the Australian telescope instead. So instead of CTIO, I'm going to select the Meckering Observatory. That's for the Prompt MO telescope. That's the only one that we can use right now. So then when I select one of these galaxies, M66, it should be okay. Remember, we're using minimum target elevation of 20 and minimum visible hours of 0.5. And you can see here that this one is very observable. Why can I not? There we go. Get rid of all these. Okay, I don't know why it's doing that. But this dark blue one is Prompt MO, which is what we care about. So then I would go through and I would select the high through filter, which is the first one. You can try to use Prompt 5, but it's not going to work because that observatory is closed. So we're going to use Prompt MO, which is the Australian one. And then we are doing a 1 exposure for 80 seconds. And that should be it. You don't have to do anything with advanced options. And that's it. So I want you all to try to go through as soon as you can and do that for as many of these galaxies that are observable. I haven't checked, but I'd assume all of them are, but I'll double check. And if you can't observe all of them, that's okay. It's an option here in this table that's telling you whether or not you did observe it. That way, if you say no, then I know that I just don't need to grade that because you weren't able to observe it. So to review, you have these galaxies, or sorry, spiral nebulae that you're going to observe. you measure the distance to them using Cepheid variable stars like you did in the last lab. And then you're going to go into Afterglow once you have your images and measure the angular diameter of these objects. That's all you're doing in this table here. You're just recording the angular diameter in arc minutes. Be careful here not to put arc seconds because we've been using that a lot. It wants in arc minutes. And then you convert that to degrees, which we've done before. Because if you remember, using this equation that we've used in the past, this angular size needs to be in degrees in order for this equation to work. So that's all you're doing there. And just to give you an example, this is a picture that I took last semester of one of these galaxies. And when you're measuring the angular diameter, you probably want to overestimate a little bit compared to what you normally would, because there's some material of this galaxy that we are not able to see, not in the visible. So you can see that it kind of extends out to here maybe. So as a good guess, I would probably measure the angular diameter as something like this. And for some reason, it didn't bring up my little, there we go. Let me try this again. Yeah, so it's giving me 516 arc seconds, but remember we want to be using arc minutes here. So 8.6 arc minutes. I would go back to the lab, put that in the table. This table here, 8.6 arc minutes, convert that to degrees. And then once I have my angular size, and I have the distance that I calculated in the previous table, I have everything I need to calculate the physical size of that nebula. And then all you're doing for the rest of the lab is just discussing it. So you talk about whether or not the sizes, the diameters of these objects are bigger than our own galaxy or smaller, and how far away they are. Are they outside our disk? Because remember, in the previous part, you found out what the diameter of our own disk is based on the distribution of all those globular clusters. So if all of these distances to these objects is super outside of our disk, that tells you something. Not only that, but if these objects are a lot bigger or comparable, at least in size, to our own galaxy, then that also tells you something. So with that information, you just talk about who was right, who was wrong, and sources of error, the whole shebang. And that's it. Really, the hardest part is probably just getting these distances down using your RR-Lyrae stars and your Cepheid variable stars. But y'all should be experts at that by now, right? So does anybody have any questions? I probably went through that a lot. Here's a question. Nope, Zach is good. Cool. Anybody else have any questions right now? Okay. So again, just to summarize, for the first part, you're going to be using RR-Lyrae stars to calculate the distance to globular clusters, and then you're going to map those clusters out in a top-down view using this, and then you're going to look at this yellow dot and see where the yellow dot, us, compares to the center of that distribution of globular clusters. And then in the next part, you're calculating the distance to these spiral nebulae using Cepheid variable stars, and you're also measuring the angular diameter of those objects using both the angular diameter, theta, and the distance that you got from the Cepheid variable stars. You're going to be calculating the physical diameter of these objects and comparing that to the diameter of our own galaxy. And that's it. So it's hopefully a lot easier than the last lab. And yeah, that's about it. I'll wrap up here. And again, if y'all have questions or if you want to just stick around and work on it while I'm here, feel free. I'll be here till 6. Otherwise, you can always email me. And anything else? That should be about it. Cool. I think that's about it. So you're free to go if you want, or you can stick around, and I will be here. Now I need to figure out how to stop the recording.